Today I am going to teach you coordination compounds. What are coordination compounds? In B.Sc second year, we will discuss about the coordination compounds and its isomeric properties. What are the isomeric properties for the compounds? First of all, we have to discuss about what are coordination compounds. Coordination compounds containing one or more complexes are coordination compounds. It means when solution of two different salts mixed with each other and formed a new salt, that compound is called coordination compound. For example, cobalt hexammonium chloride. Another example is copper tetrammonium with platinum tetrachloride. The next another example is platinum diammonium chloride. Coordination compounds formed by the covalent bond in which the coordinate part is prominent between a metal ion and a ligand surrounding this metal. Many of the coordination compounds are brightly colored because the coordination compounds of transition metal series majorly formed colored compounds. What about salts? We have different types of salt. For example, NaCl, ammonium chloride, ferrous sulfate, and the nature of these salts is of single salt. We have another variety of salt are double salts or complex salts. What are double salts? Here we can define these two types of salt in a separate sheet. First, what about double salts, which lose their identity in the solution? When dissolved in water, they give a specific test of each constituent ion. If, for example, we have chloride in our salt, then we can get a chloride precipitation with its specific test. For example, ferrous ammonium sulfate, when dissolved in water, it gives ferrous sulfate and ammonium sulfate. Whereas the complex salts, which do not lose their identity. Identity means they are separate parts of the salts that can't be identified. When dissolved in water, they do not give any specific test for each constituent ion. For example, potassium hexacyanoferrate, in which when we dissolve this hexacyanoferrate in water, then only we can get the test of potassium, because potassium and the centrally located metal ion with cyanide, that can be separated out, not the ferrous and cyanide ion. In which what is complex ion? Electrically charged ion formed by the combination of a central metal atom or ion and a suitable number of neutral molecules or anions. For example, ferrous hexacyano compound, in which the complex with a net charge on this ion is complex ion. We can define it as a complex ion because in which a central located ferrous metal atom, which is in the form of ion, and the suitable number of neutral molecule or anions. Anions, here we are using cyanide. So hexacyanoferrate, this is the complex ion. And what about the complex charge? We have seen here in the previous slide that 3 negative is already present on the complex. The charge on the complex, that is equal to the sum of charges on the metal and the ligand. Suppose we have hexacyanoferrate, in which iron containing +3 oxidation state, whereas cyanide has its valency of -1. We are using here 6 cyanide ions, which gives the total of -3 charge on this particular complex ion. For the neutral charge on the complex, it is the sum of charges on the metal, ligand and counterbalance ions. The counterbalance ion is balanced by its primary valencies. Here we are using chloride as a primary valent atom. So knowing the charge on a complex ion and the charge on each ligand, one can easily determine the oxidation number of metal. If we know the oxidation number of metal, then vice versa we can calculate the charge on the complex ion. So vice versa we can calculate both the things. If we are knowing about the charge on the ion, then we can calculate the oxidation state, or if we know the oxidation state of a particular metal ion, then we can calculate the charge on the complex ion. There are several terminologies that we are using in the coordination compounds. To define these terminologies, we have to discuss some of them. First, ligand. What are ligands? We are here using several types of ligands. A neutral molecule or ion which surround the central metal atom or ion in a complex. For example, water, ammonia, carbonyl, hydroxyl, fluoride, cyanide, and oxalate. I have told you that neutral molecule or ion which surrounds the central metal atom or ion. It means in a central position there is a metal ion or metal atom present in a particular periphery, and around the central metal atom we are having some neutral or molecule or atoms or ions. For example, water molecule. It is a neutral molecule containing lone pair of electrons to form the bond between the metal and the ligand. Similarly, we are having here ammonia. Ammonia is also a neutral ligand. Along with this, we have carbonyl. Carbonyl also having some lone pair of electrons that can be used as a coordinate bond. Also, hydroxide ion or hydroxide molecular ion can also be used as a ligand which can form a bonding between metal and particularly hydroxide ion. Also fluoride ion, cyanide ion, these all are anions that can be used as a ligand for the bond formation between metal and the ligand. Now, depending upon the donor sites of atoms, these ligands can be classified into different parts. For example, if we are having one donor site, then it is called as monodentate ligand. For example, hydroxide ion. In hydroxide ion, we have one bonding pair of electrons that can be used for coordinate bond between this particular hydroxide ion and a central metal atom. Similarly, if more than one donor sites are available, for example two donor sites are available, then it is a bidentate ligand. For example, ethylene diamine or oxalate ion. The third one is polydentate ligand. Polydentate ligand which have two or more than two donor sites. Poly means more than one, many sites. So in polydentate ligands we have many sites which can donate its lone pair of electron or bonding pair of electrons to the central metal atoms present in the centrally located position. The molecules which contains two or more donor atoms on the same molecule, then they are called as chelating agents. It means the donor sites available on a particular ligand and the number is more than two, then they can be called as chelating ligands. What about the coordination sphere? We have a coordination sphere also in our coordination compounds. What is that? The coordination, the complex compounds that is written in the square bracket composing of the central metal atom and the ligands attached to it is called its coordination sphere. For example, in the previous slide we have discussed some examples of the coordination compounds. Here also we have nickel tetracyano. In this compound we have nickel at centrally located position and the ligands surrounding it in the form of cyanide ion, and this is called coordination sphere. Outside this coordination sphere, we are putting the charge on the complex ion. Now next is the coordination number. What is the coordination number? Why we are calling it as a coordination number? The number of coordinate bonds formed by the ligands with the central metal atom or ion. For example, nickel tetracyanochloride. Here the coordination number is 4. In the next example of chromium, here we are having coordination number of 6 because the number of ligands donor sites are 6 here. 2 of ethylene diamine, 1 from amine and 1 from bromine. 1 and 4 from ethylene diamine means the total 6 coordinating sites are occupied by the ethylene diamine, ammonia and bromine. So that's why its coordination number is 6. What are chelates? Now we will take some few minutes for discussing this chelate. What are chelates? The cyclic compounds formed when a multi-dentate ligand attached through 2 or more donor atoms to the same central metal ion. For example, ethylene diamine. We have discussed it in the previous slide. Ethylene diamine. In this, we have 2 donor sites in the form of nitrogen atom, which contains 2 non-bonded electrons, which can be donated through coordinate bond to the copper. Here, ethylene diamine, when coordinating with the copper, it forms a pentacyclic structure. Here, it is shown in the form of pentacyclic structure. This is a chelate formation. Means the complex compound formed when a multidentate, it is a multidentate ligand attached through 2 or more donor atoms. It is attached through 2 or more donor atoms. These are 2 different donor atoms at the same metal ion that we have discussed here. In nature, we have also some examples of chelates. For example, porphyrines. Porphyrin is another good example of chelate formation. We have chlorophyll and heme group. Heme group in our hemoglobin that forms our blood. It provides extra stability to the complex due to its ring formation. As we all know that the ring formed during this complex formation, it is more stable than monodentate or bidentate ligands. Now come to the Werner theory of coordination compound, which is of most important part of this coordination compound. In 1893, Werner gave a theory to explain the structure of coordination compounds, in which metal possesses 2 types of valencies. First is primary and another one is secondary valency. What about primary or secondary? How we can define these 2 types of valencies? The primary valencies are ionizable. These can be ionized in 2 forms, in separate forms. Whereas the secondary valencies, these are non-ionizable forms. Second, the primary valencies are non-directional. They have no direction. They can be placed in any spatial arrangement. But whereas in secondary valencies, these are directional. The primary valencies are satisfied by negative ions, whereas the secondary valencies can be satisfied by negative ion or neutral molecules. Primary valencies, on the other hand, can be known as oxidation state. We have discussed previously in our previous slide that there is an oxidation state in the complex compound. This oxidation state is satisfied by the primary valency, whereas the secondary valency, which is known as the coordination number, that can be 4, 6 or 8. The primary valency, because it is a non-directional valency, it does not provide any idea about the geometry of the complex, whereas the secondary valency determines the geometry of the complex because it has its definite and specific orientation around the central metal atom. The negative ion may satisfy both the primary and the secondary valencies depending upon the nature of bonding between the central metal atom and the ligand. If it is a multidentate, then it can satisfy it through primary valency and secondary valency. Sidwick also give an electronic interpretation of coordination compounds, which is of immense importance. In a coordination sphere, whole of the coordinate compound can be described through this Sidwick electronic interpretation of coordination compounds. Here the centrally located is central metal atom, that is cobalt. Around this cobalt central metal atom there are specific ligands. What are these specific ligands? These are filled by the primary valency and the secondary valency. Primary valency here we have shown by the red color and the secondary valency through the black color, and this square bracket is known as the coordination sphere of the coordinating compound. The primary valencies that are ionizable results from the transference of electron and it is formed by the ionic bonding, whereas the secondary valencies that results from the sharing of electron means there is a coordinate bond present in between the metal atom and the ligand. Here we are having 1, 2, 3, 4, 5, 6. 6 valencies are satisfied by the secondary valencies in the form of ammonia, and these are connected through central metal atom by coordinate bond. Now the IUPAC rules for nomenclature of coordination compounds. It is also of such importance that we are having almost every year some questions on this IUPAC nomenclature of coordination compounds. First of all, we should know the order of naming of these cation and anions. The order of naming of ions is the cation are named first, followed by the anions, and that should be in an alphabetical order. That should be in an alphabetical order. That should be followed, and only then we can write the correct IUPAC name for the coordinating compound. Next point is, when naming a complex, when we are giving a name to the complex, then ligand should be named first, and that should also follow the alphabetical order. Second, the metal atom or ion should be named last, in which the oxidation state should be written in Roman numerals. These rules are accepted by the International Union of Pure and Applied Chemistry, and that are acceptable at the international level. So we have to follow these rules strictly to get the right name for the coordination compounds. For example, we have triamine trichloride cobalt compound. Here we have written cation named first, followed by the anions. We have cation in the form of this cobalt, in which the ligands are named according to the alphabetical order. First amine, then chloro, and then the metal atom would be considered for naming the ion. Now, how we can name about the ligands? We name about the ligands according to the suffix we have fixed for their position. The naming of the ligand. Name of anion ligands ends with suffix O. For example, if we have anion ligand in the form of fluoride, then E should be replaced with O. If chloride, then chlorido. If we have hydroxide, then hydroxo. We have cyanide, then cyano. If we are containing a ligand named ends with IDE, then the suffix ends with O. Similarly, if we have ite in the end of the name of any ligand of anion, then it ends with the ito, I-T-O, ito. For example, here we have sulfite. Then the name should be written strictly according to the IUPAC nomenclature, and it is accepted in the form of sulfito. If we have ate at the end of a ligand, then suffix ends with the ato. Sulfate, then it ends with the O, sulfato. Thiocyanate, it ends with the thiocyanato. If we have oxalate, then it ends with the oxalato. Now the name of the cationic ligand ends with the suffix em. For example, if we have nitroso, then nitrosonium. If we have nitro, means nitronium. If we are having hydrogen in the form of ligand, then it is named as hydrogenium as a ligand. If we are having some neutral ligands, then they can be named as such. For example, pyridine. Pyridine can be named as pyridine. If we have ethyl-diamine, then ethyl-diamine written as such. For water, we use aquo. Aquo is another name of water. Ammonia, then ammonia can be written as amine as such. The neutral ligands are named as such, like CO, carbonyl. Carbonyl would be written in the ligand form as a carbonyl. There are other certain rules that we have to follow for naming the coordination compounds. Greek prefixes should be used if one type of ligand occurs more than once, like di, tri, tetra, penta, hexa are used to indicate such numbers. For example, if we are having one type of ligands more than one time, then if we have two, then we are using di. If we have three times ligand, then it is named prefixes in the name of tri. If we have repeating four times a ligand, then we have tetra. Similarly, penta and hexa used for 5 and 6 respectively. If the ligands already contains Greek prefixes like di, tri, tetra, penta, in a ligand, if we already have these type of Greek prefixes, then we have to use prefix of bis for 2, tris for 3, tetrakis for 4, pentakis for 5, hexakis for 6, etc. Alternate prefixes are used, and the name of the ligand is placed in parenthesis, means a small bracket. The naming of a complex ion. How we can name a complex according to the IUPAC nomenclature? First, ligands are named first, followed by the central metal atom. Means if we have a complex, then their ligand name should be given first and followed by its central metal atom. Whereas in cationic complexes, the central metal atom is named as such, followed by its oxidation number in Roman numeral. For example, if we are using a cationic complex, then we have to name ligands, then its central metal atom, and after that the oxidation state of that central metal atom should be written in a Roman numeral in a small parenthesis. In anionic complexes, a suffix 8 is used to the name of the metal. For example, if we have ionic complexes in the form of metal, then titanium should be written as titanate, iron should be written as ferrate, copper must be written in the form of cuprate, whereas chromium, chromate. Another example of like scandium, you must write like scandate. Molybdenum should be written in the form of molybdenate. Here are some examples for the cationic complexes. It is CO, NH3 6. Outside the coordination sphere we have 3 chloride ions in the form of primary valency, and it should be named as hexaamine because ligand named first. Hexaamine, hexa is used for the 6. We have 6 amine molecules. Hexaamine, cobalt. 3 is the oxidation state, that is followed by the cobalt metal ion, and in the last we write the anion chloride. Next example is copper, Cu, NH3 4. Outside the central coordination sphere we have sulfate. So we should give a name to this particular compound like tetraamine because ligand should be named first. Tetraamine. Copper 2 is the oxidation state, that is followed by the copper metal ion, and sulfate, the anion should be given in the last. Here is an example of chelate compound, ene, because ethylene diamine already contains di in its name. So how it should be named? It should be named as tris because we have 3 ethylene diamine molecules coordinated with the chromium. So ligand should be named first. It is tris 3, tris ethylene diamine. After that metal ion, chromium, and then its oxidation state 3, which is +3, and in the last chloride as a primary valency. Another example of this chelate compound is pyridine. It is tetrakis pyridine because 4 molecules of pyridine is directly attached with the platinum. Tetrakis, pyridine, platinum 2 chloride. The next example is which is of multi-ligand system. Here we have amine, aqua, pyridine, and nitro groups attached with the centrally located platinum atom. So we should give the name according to their alphabetical order. First, amine. We have 1 molecule, so we are writing here amine, 1 water molecule, that is aqua, another nitro, pyridine, only 1 molecule of pyridine is present, platinum, centrally located metal atom, and then its oxidation state of 2, and then anion chloride. The name of this particular compound is amine, aquo, nitro, pyridine, platinum 2 chloride. The one more important thing that all should be remembered at the time of giving the name to the coordination compound, that is we have to write the name of the complex within a line. We do not have to separate these ligands or metal or oxidation state in a separate way. It should be a one word name. I am repeating it, it should be a one word name. The examples of anionic complexes, K4, FeCN6, that is, first we have to give the name to the cation, that is, here it is potassium, so we have given the name to the potassium. Then come to the anion. In anion we have 2 parts, a ligand and a metal ion. In this anionic complex, first we have to give name to the ligand, that is hexacyano, and then followed by the ferrous, that should be given name as ferrate, means potassium hexacyanoferrate. Then its oxidation state, that is of 2. The next example is of hydrogen, which is a cation, hydrogen hexachloro. Hexachloro is the ligand, and then platinate 4. Next example is potassium trichromato. Here is the ligand trichromato. Potassium trichromato iridate, because if we are having metal in a anionic complexes, the metal name should be ends with the 8. The metal name should be ends with the 8. Here is an example of anionic and cationic complexes. We have to start with the left hand side. In this case, if we have anionic and cationic complexes, here in the left side we have hexamine cobalt and its oxidation state of 3. On the right hand side we have trioxylato chromate 3rd. Next example, tetraamine platinum, its oxidation state is 2. Then tetrachloroplatinate 2. In these type of examples where anionic and cationic complexes are present, then the second one should be given its name with the 8, whereas the first one should be written as such of its name. The factors affecting the stability of complexes. There are several factors that affect the stability of the complexes, in which the first is the nature of the central metal atom or ion. If greater is the charge density, then greater is the stability of the complex. If we have a central metal atom and the charge on its central metal atom is greater, then its ability to combine with the ligand is greater than that of the central metal atom containing lesser number of charge. If we have one example, suppose we are having a complex of Fe plus 3 or Fe plus 2, then Fe plus 3 have more tendency to get attached with the ligand, whereas Fe2 have less tendency to get attached with the ligand. So that's why the stability of the Fe plus 3 complex is greater than that of the stability of the Fe plus 2 complex. The next example is of chromium. If we have chromium 4 and chromium 6, then chromium 6 complex would form a stable complex with the ligands in comparison to the chromium 4. Now the next is the nature of ligands. Nature of ligands is also important for the stability of the complex. If a certain ligand has its tendency to give its electron easily to the central metal atom, then it is a strong nature to bind with the metal atom, and it has a strong complex. For example, cyanide has its strong capability to get bind with the metal atom, whereas aqua, water molecule, has lesser tendency to get attached with the central metal atom, in which cyanide form a stable complex in comparison with the water molecule. If we have a ligand of such type that can form a chelate, then it can also increase the stability of the molecule. So the chelate effect is also an important factor for the stability of the complex. If certain compounds makes chelate formation, then the compound would automatically be more stable than that of the monodentate or bidentate or tridentate. The size of the chelate plays an important role for the stability. If we have 3-membered ring formation, then it would be a lesser stable complex. If we have 4-membered ring formation, then the stability would increase, whereas the 5-membered is the most stable form of chelate. and it would form a stable complex if we have 5-member chelate ring in comparison with the 2, 3 or 4-member chelate formation. And that's all. Thank you very much.